La segunda plática de McDonugh, que nos va a estar hablando sobre geoneutrinos y la producción de calor en la Tierra. Ya a todos les presenté desde el lunes al doctor McDonugh. ¿Sí nos escuchan todos los que están conectados? ¿César?
Sí, muy bien.
Ya. Ok. Bueno, entonces vamos a comenzar. ¿Dio? Ok. Yes, you can. So you can stay somewhere around here so they can.
Okay, I can do that. Well, thank you. Let me just give a couple minutes to say. First off, I'm having a fantastic time. It's like a science party for a week. I really am impressed. I've had some very fun conversations. Last night, I had a great party. I was out with the graduate students and we had lots of fun. We talked about lots of things. We had beer and pizza and other things. That was really fun, and thank you for setting that up. I'm also extremely impressed by all the equipment that's at this department. It's really great opportunities to do science, and I'm trying to think about how I can collaborate. It's really fun to be here. Thank you for this. Now I want to talk about something entirely different, really something that excites me. And for the students in the room, you know, I guess my career is at least 35 years along. And I don't think I planned to become a geochemist, but that happened. And in 2005, I definitely did not plan to become a geoneutrinologist, whatever that might be. But the start of this story is just as useful as the story itself. So in 2005, I received a request from Nature magazine. Would I review this paper? And I looked at the title, and I looked at the contents, and I sent it right back minutes later and said, I don't know this topic at all. They sent it back to me and they said, we would like you to review it. So I spent a bit more time on it. And I sent it back a second time saying, I don't know what's on the x-axis and I don't know what's on the y-axis of most of the diagrams. They said, we need a geological expert. So for the third time, I said, I will do this. And I called up Jordan Goodman, who is a particle physicist. And one of the benefits of being at a university is that I was on a committee once with Jordan. And so Jordan said, well, what's the title of the article? And I said, Jordan, I'd like to work with one of your graduate students. It's probably, you know, not worth talking about this. So I read the title and he says, please come to my office right away. So this was exciting to a particle physicist at the University of Maryland. The other advantage throughout all this time, I was immediately, I wrote my review. I couldn't understand much of it. I propagated the uncertainties. And then I said, I think I understand, but in fact, they had 25 counts plus 17 counts minus 18 counts. And my estimate of their uncertainty was they had 25 counts plus 17 counts minus 16 counts or something like this. So it was very, very close. So about a week later, I'm sitting at 5 o'clock in the afternoon in my house and I get a phone call. Hello, this is John Learned. We know what you did wrong in your calculation. It was one of the authors of the paper, and I don't know how they knew I was the reviewer. And so we had this conversation. He says, I would like you to come to Hawaii, middle of December, for a meeting. Who turns Hawaii invitation down? And ever since that, I've been treated wonderfully by the particle physics community. I feel like a graduate student, and they educate me. So I will do my best to give it back to you. I will tell you a story today about why the geoscience community might be interested in geoneutrinos. I think it's very, very fun. Oh, maybe just take one step back and say, well, in fact, Bedja Roskovich is a particle physicist. And you'll see a picture of Bedya. Laura is my present student, but I've had 3 PhD students working on the topic. And Andrei Sharamek was my postdoc in 2011, 2012, 2013. And Andrei, he had just finished a postdoc at University of Colorado, Boulder. And he perhaps boldly asked me, I'd love to be a postdoc with you, but can I stay in Boulder? And I said, sure, why not? So I traveled to Boulder a couple of times, which I really enjoyed. It's a beautiful city. And he stayed in Boulder, and we began a practice of calling each other at least once or twice a week by Skype, and we've done it ever since. So and by the way, Andrei is a geophysicist. He's typically involved in convection of the Earth's interior. So I hired somebody as a postdoc who had nothing to do with my science. So many of us study the Earth, like to understand what's going on inside the Earth. And we like seismology because it's sort of like when a mother-to-be goes to the doctor and uses an ultrasound device that essentially sends acoustic waves into her uterus, and it's both the transmitter and the receiver, the head of the ultrasound instrument. And we image infants. And seismology has imaged these things called LLSVPs, large, low, shear velocity provinces. And like all of us in this room, we have a creative juice that will say, I bet I know what that is. Most of us are wrong, including me, but this is where geoneutrinos can come in to help. We have a seismic signature, and then we have a cartoon, and we may actually ultimately map out the mantle with geoneutrinos and be able to see if one matches the other. So here we have a cartoon talking about the viscosity structure. Ed Geoneutrinos, one of our most famous seismologists and artists in the community, makes these images of LLSVPs giving rise to mantle plumes, while at the same time we have subducting slabs coming out creating something else. And then Barbara Romanovich has provided us with seismological images of the Earth's interior. However, my point about geoneutrinos is really going to focus right here. And I think this is the most important point. This is the blue Earth as we know it. If we put our hands on the blue Earth, we note that it is emitting 46 plus or minus 3 terawatts of power. And this number was initially established in the 1960s and has been reestablished, and reestablished, complete with uncertainties. And it's really varied from about 42 to 47 terawatts over that period of time, more than a half a century. And the uncertainty here is really based upon about 40,000 downhole temperature logs that we have, about 20,000 in the ocean and about 20,000 on land. So it's a good, well-known number. And why is this important? Because this is the energy expressed from the Earth that drives plate tectonics. And this is an image that says the LLSVPs deep in the mantle may actually be emitting geoneutrinos, and we're prepared to test this hypothesis. So let me frame it for you. Geoneutrino detection can help us evaluate the fuel tank in a hybrid car. So I've had the opportunity to be in a Prius, even while I've been here. And this Prius has 2 fuels. It has a battery power and a petrol power. The Earth is no different. But the situation for the Earth has a question mark because we do not know where the fuel gauge is for the Earth. We do not know how much fuel we have left to run the Earth's engine. We're talking plate tectonics. We're talking mantle convection, the geodynamo, volcanism. So this is a question really about what are the fuel gauges for the primordial energy and the nuclear energy. Oh my heavens. That should be over here, and that should be over there. I'll do that on my next talk. But really, that's the question. We know we have 46 terawatts of power. We know the size of the Earth, the incoming velocity of meteorites, about 20 kilometers a second. You can just take 6 times 10 to the 24 kilograms and 20 kilometers per second, and you'll calculate that the Earth, by building an Earth, you would have started out with 10 to the 32 joules. You could form the Earth's core, and the gravitational settling will give you 10 to the 31 joules, so you can forget that. It's an order of magnitude less. But what the real question is, how fast did we dissipate from the conductive core through the insulating mantle this primordial energy from the Earth? And then likewise, we have models for how much radioactive energy in the Earth, and believe it or not all of geology agrees with each other. Now, let us put together this in a context. So I was playing a little with imagery right here. But the Earth today shines with 10 to the 25 geoneutrinos per second. So you can consider the Earth, and an article was written in 1990. The Earth is an anti-neutrino star. Now, we cannot see these anti-neutrinos coming out. And in this room, there is 6 million per centimeter square per second coming up through the interior passing through it. Okay, now let me frame it a little bit further in terms of the impact. So I got up early in the morning to watch the announcement because my friends told me they had nominated a couple of people for this Nobel Prize. But the Nobel Prize in 2015 went to neutrino scientists. And boy, did I jump for joy when the third slide said, neutrinos are very common fundamental particles, solar, atmospheric, and I saw geoneutrinos on the screen. And that's how important we're really talking about doing world-class science. And it's been a very, very wonderful collaboration with particle physicists. They also appreciate what we're trying to do. So here's the fundamental. The nature and the amount of the Earth's thermal power. Radiogenic heating versus secular cooling. Secular cooling just means how fast we dissipate our primordial rate. So what can we address with studies in geoneutrinos? Well, for this first one is the abundance of heat-producing elements in the Earth. Potassium, thorium, and uranium make up 99.x, I can't remember that number, but it's like 0.2, 99% of the energy from radioactive decay. About 40% from uranium, 40% from thorium, and 20% from potassium. Okay. Now, if we know that, we have several people who have estimated bulk silicate Earth, and that is to assert there's none of these elements in the core. But the estimates go from 9 to 36. The best way I think of thinking about that is 20 plus or minus 10. So it goes from 10 to 30 for the most part. And we would like to narrow that down. A factor of 3 difference is really big. Clues to planet formation. It constrains the chondritic Earth models. Constrains in the sense, oh, please, come on down front. There's some nice seats in the front. Nobody ever likes going to the front. Clues to planet formation. This actually helps us to understand whether or not we're orange, chocolate, or strawberry type of chondrite, building blocks. A lot of times people will argue that we look like the ENSTA-type chondrites in terms of isotopic signature. Geoneutrinos can actually give us insights in that regard. What were the building blocks? The amount of radiogenic power to drive mantle convection. Now this is really interesting. We fool ourselves sometimes. We think we know the composition of the continental crust. And I'd say we've got that one reasonably well understood, but we don't have the uncertainties pinned down. If we understand the Earth's composition, and it goes 20 plus or minus 10, models that suggest 10 ppb uranium, which is equivalent to 10 terawatts of power, if you have the continental crust with 7 terawatts of power, and you put in the uncertainties, you have numbers that get down to 1 terawatt of power from nuclear decay in the mantle. if you then say we have a 36 terawatt Earth, you can get up to 28. So what you can see is our knowledge base essentially is a factor of 3 for the entire Earth and a factor of 30 for how much power is driving mantle convection. We should do better than that. Okay, so that's where we're at. And then finally, at the end, I'll highlight a little bit on layers and some hidden structures deep in the Earth's interior. And I might not know the origin, but if I can, I'll map out the uranium and thorium distribution in those things. So my friend here says, geoneutrino studies is the future in our science. All right, so as I said, 10, 20, 30 characterizes the dominant models that are out there arguing for what is the composition of the Earth. And by the way, 10, 20, 30 could also be an expression of parts per billion uranium, 10, 20, 30. It's just magically, it turns out that you can multiply the thorium-uranium ratio of 4 and the potassium-uranium ratio of 10,000, and that ends up being 10 terawatts, 20 terawatts, or 30 terawatts, depending on 10, 20, or 30 parts per billion uranium in the silicate fraction of the Earth. Handy. So we've been calling them low Q, middle Q, and high Q models, just to give it some sort of flux. And what I'm showing here is the blue would represent the continental crust. And it's been identified here as contribution to the upper, middle, and lower. Approximately 7 terawatts of power is locked up in the continental crust. If it's locked up in the continental crust, then it's not in the mantle and it cannot drive plate tectonics. Okay, so then the red says 6 and 3, we're getting up to 10 here, 13 and 7, we're getting up to 20, and likewise we get up to 30. So there's two components, what's in the crust and what's not in the crust. And then we can get to the surface expression of 46 terawatts, and we say this is the radiogenic contributions. And the other is a expression of the secular variation. So really we're looking at the contrast between how much of this and how much of that. That's those two fuel gauges. And the principal point of takeaway is our present understanding is a factor of 3 between models for the composition of the Earth and a factor of 20 at least for the models in the mantle. Now, I've spent a fair amount of time talking about radiogenic power, but I can make this expression. Radiogenic heat flux is equal to the geoneutrino flux. Very much proportional. There's a few mathematical symbols in between, but you can just say one is directly proportional to the other. And so these are the radiogenic contributions. Lot from uranium, lot from thorium, 40, 40. This is 20%, potassium 40. And you can see here there's tiny amounts of energy coming from rubidium decay and 147 samarium. And equally trivial is the 235 uranium. You're driving nuclear power plants with 235 uranium, but there's very little left. There's 1/140th uranium 235 relative to 238. However, the term proportional, you have to understand that 70% of the neutrinos coming out of the Earth are from potassium. And that's really a function of how many parts per million potassium and what is the rate of decay of potassium. So that explains that proportionality. But these are the three big players, potassium, thorium, and uranium. Potassium has two contributions. These are called antineutrinos and these are called neutrinos. And I'll explain that in a minute. This is Andre, my former postdoc in the early part of this decade. Here is me and my constant, I always wear a tie. Even though this is my apartment in Sendai, Japan, and it's about 8 o'clock at night. Yeah, that was the way I was. Went to Catholic school when I was a kid. Here is Bedya, he's a particle physicist, and Ingrida, she's a particle physicist. And we meet every week. In fact, it was Juan Pablo helped me to make sure I was at the weekly meeting on Monday for this same event. And then there's my graduate student, Laura. And in fact, it's a family affair. So this is my wife, Hiroko. She's a particle physicist. And then Yufei, I've worked with Yufei since about 2012. She's here in her office at Caltech, but mostly she has an office in Beijing. And we meet all the time, and we talk about all sorts of things weekly. Now, what I have here is, I'll go back to this diagram at the end of my talk, but I have, again, a y-axis and an x-axis. The x-axis is what we can do. And so I'd like to highlight, a good portion of my talk is going to say, what can we do for geoneutrinos? The y-axis is total measured flux in TNU. Oh my heavens, what a crazy unit. This is actually the value that comes from the particle physics experiment. TNU stands for terrestrial neutrino unit. And for those of you who do geochemistry, say you go downstairs and you want to use one Pavlov's mass spectrometer, and you measure neodymium isotopes in a rock that everybody has, and you get this value, and somebody measures neodymium isotopes in a rock with a similar but different machine, and they get that value. Well, this is already known, and we just normalize it to the same value. And that's exactly what's happening in TNU. Sometimes we have half a kiloton device detector, sometimes we have a kiloton detector, and sometimes I'm involved in a project with the Chinese. We're trying to build a 20 kiloton detector. So the signal you get, the size of the detector will change the signal you get. And so we use this as a way to talk about all detectors, the detector efficiency, et cetera. So that's all that unit means. And let's just say it's the flux that's coming out of the Earth. So we get a value, and this is the singular value for the Camland detector in the Alps of Japan. These detectors are 5 to 8 times bigger than the size of this room, and they're usually about 1.5 kilometers underground, and they're 24 hours a day, 365 days a year, working all the time to detect the signal. And just to put it in perspective, the kiloton device that's in Camland gets about 10 counts per year. Okay. So what we have on this x-axis, they're just offset, but they're offset in this axis, but they're not really offset in that axis. It's just this axis, they're all at this dashed line. I dropped a couple of the figures down so that you could see them. And the names are not important. It could be like the first 4 people in this row. Enimoto, Fiorentini, Huang, and Ceramic have all estimated what is the concentration of uranium in the local crust. Now, I don't have to do it, but I could go outside, and I can tell you that the dirt outside has approximately 3 parts per million uranium. And I'd be so confident as to make you buy the next beer if you say it's a half a ppm, because I go, no. It's definitely going to be about 3 plus or minus 2, in fact, just to make sure I give you a number. So what we have is some really smart people, and they have tried to estimate what is the amount and distribution of uranium and thorium around the detector. And a couple of my slides will show you the details at which we do this. And that information will tell us how much uranium and thorium is in the Earth. So that's where geology comes in. We really need to get this right. And if we say it's there, or there, it comes out to, these are all the estimates of how much is in the mantle. The mantle flux would then be 10 TNU out of the 40 TNU. And you can see that it's, and I'll show you in the end, the most recent results we have say it could be 0 TNU to about 20 TNU. We're in an immature science at the moment. What are geoneutrinos? Well, this is really what's called the fermion diagram. But we'll see that neutrons and protons are made up and down quarks. We're all familiar with the electron. In fact, when we take a sweater off and we get a static electricity, the electron reminds us that it's alive, it's there, it's ready to cause charge. And in fact, we'll often be hit by a photon that might come from that event, in that little spark that you potentially have. Well, a neutrino is a lepton, just like the electron. And you would all know the electron, and most of you might even know a thing called a positron. And a positron is the antimatter component of the electron. It is identical to the electron, except having a positive charge instead of the electron's negative charge. And so there are neutrinos and antineutrinos. Neutrinos would be matter, and we are in a matter universe. And antineutrinos are antimatter. So it would be the equivalent of talking about the positron. Okay? Now, where the heck do they come from? So this is a schematic of what is a standard neutron and what is a standard proton. And I'm talking here about beta minus decay, which is extremely common. Now I list there thorium, uranium, potassium, rhenium, lutetium, rubidium. There could be more, for instance, carbon-14. Now most people realize that uranium goes through alpha decay, thorium does alpha decay. But also, occasionally, it goes through beta decay steps. And what is happening during beta decay? Well, it could be beta minus or beta plus, but in this case, I'll go beta minus. And that is when a down quark transforms to an up quark. That transformation is actually accommodated by this W minus boson. It's a weakly interacting force carrier. And what comes out during beta minus decay is an antineutrino and electron. So the first quarter of the last century, when particle physicists were understanding radioactivity and radioactive decay, they had actually identified beta minus decay as electron emission. And Wolfgang Pauli had come out with the sort of regretful statement, I will not go to your conference, but I will send my graduate student, and he will tell you that regrettably, I'm going to suggest that there is a particle that comes out during this decay process, but we will never be able to measure it. And that is a statement that he had made in the 1920s conference presentation. It was several years later that Enrico Fermi called this the neutrino, or the little neutron, because it was a neutral particle. And it was in 1956 that Reines and Cowan were able to detect it coming out of nuclear reactors, which are very large beta emitters. And that's where we got the fundamental understanding of these particles. This is the challenge I faced when I got the Nature article. It had neutrino energies and MEV. Yeah, I could probably say I understand that. And then it said detection rate in kiloton year per keV. I went, no, I don't understand that. But I just said energy, for anybody who does X-ray analysis like on electron probe, this is energy versus intensity. That's all it is. And then we have two contributions. This might be like the Compton background. This is just the background from the nuclear reactors. And then this is our signal. This black one comes from uranium-238. This is one beta decay step. This is a different beta decay step. And then this is the thorium signal. And they're right on top of each other. There's two thorium beta decay steps we can count. But if we can quantify this entire area under the curve, we can tell you what the flux is. And that's what has happened. And this is what I had this in a paper, and I said, this is an ideal spectrum. It assumes thorium uranium equals 4. And the closest reactor is about 1,000 kilometers away. And the closer and closer and closer I bring the nuclear reactor, this thing grows like a mountain, and this goes down. So the field has really been alive for 15 years. So there was a Nature paper in 2005, which I was able to not only review, but they asked me to then later write up a news and views for what it means. And so I did my best at that. Actually got me into a legal battle with a crazy guy that wanted me to sort of adopt his idea that there's a nuclear reactor in the center of the Earth. My university finally had its lawyers write a cease and desist sign. That's how crazy this field could get. So 2011, 13, and 16, the Japanese have come out with results from their experiments. And the Italians with their experiments have come out, including this year, with their estimates for the flux from the Earth. Now what we end up having is 2 different brown colors and really 3 different green colors. And they're representing what we best expect to be the contributions from the different portions of the Earth. The closest 500 kilometers is a very important signal. The rest of the crust around the world, let's say the crust in Mexico and all of its uranium in, and then the entire mantle signal. And we have these high, medium, and low contributions. So the x-axis is just really the dates the experiments have come out. Perhaps for me, I was excited in the 2016 preliminary data from the Japanese group, CAMLAB. They were actually able to, this is the estimate for the bulk silicate earth thorium uranium ratio, and this is the molar ratio. So the weight ppm to ppm for the earth might be, well, it'd be 3.8. But if you take the atoms of 232 to the atoms of 238, it's 3.9. And then this would be the uncertainty from our chondritic information. And then this is a chi-square misfit, and this is the mass ratio that was actually measured by the detector. And what you can see here is minimize, the best fit is here, and at the 1 signal limit, we're still within the bandwidth of the chondrites. Well, the answer that they published is that they get a value of 4 plus 5 minus 3. You might think that's crazy. We know it better than a factor of, well, 100% uncertainty. However, Fogley et al. In 2010, PhysRev Reviews, published the sum of all data was 26 plus infinity minus 0. Actually, they reported as minus infinity, and I just don't understand minus infinity. So in a very short period of time, between 2010 and 2016, we changed the story. And in fact, the Chinese experiment, when it comes online, perhaps in 2022, after about a year's time, they will get about 15% uncertainty. And after about 10 years' time, they should get below about 6, they should get to about plus or minus 6% uncertainty. That's a global measurement. Something, you know, I might, in my dreams, sort of say, oh, it's this for this reason and this reason and this reason. But now I have a way to test how dreamy I am. So as geologists, we put together maps, and these maps are the distribution of rocks on the Earth. And this is an estimate that is the distribution of neutrinos. And as you watch this go around, every once in a while, you'll see the Himalayas show up as a bright neutrino emitter. It is simply proportional to the thickness of the continental crust. The continental crust, well, like I said, we go outside and there'd be about 3 parts per million uranium. If we think about the average crust, it's about 1 part per million uranium. And we think about the mantle, it's about 10 parts per billion uranium. So the mantle is a weak emitter, the crust is a strong emitter. And the signal really scales with thickness of the crust. And TNU, well, these are again the units of terrestrial neutrino units. So now I try to just make it reasonable for why it might be important to you. And really, we were trying to measure the amount of thorium uranium in the thorium uranium ratio in the Earth. Now, I said the most amount of neutrinos coming out of the Earth are from potassium. And there are the details in the detection, but we use a detection method called the inverse beta decay method. But basically, the neutrino that comes from potassium does not have enough energy to hit a free proton and to break it into a neutron and a positron. That's how we detect them. So it's what we call an energy threshold, and potassium neutrino is below the energy threshold. I'll be going to a meeting October 20 to 24 in Prague, and this is the 7th Geoneutrino meeting. And at that meeting, there will be 2 physicists who will be talking about possibilities from detecting potassium geoneutrinos. So the physics community is working hard to see if they can measure potassium geoneutrinos. So what I now say is I'm going to switch to understand the continental crust and its composition. How does it help and how it defines the unknowns? Okay, so this is a standard job that I have that for the last 15 years I've been working on. And to put it in perspective, it says here the geoneutrino signal in TNU scales as a function of how far away it is. The easiest way to think about this is I can see the uranium atom that's in the front row much better than the uranium atom in the back row, because that can have a particle that can go, and you can just think of the cone and not steroids, steradians. And you can think about what's the probability of an atom that's starting here hitting me versus an atom starting there hitting me. So it's a 1/r² relationship in terms of sensitivity. And so the first 500 kilometers, right about here, typically gives 50% of the signal. Know the first 500 kilometers quite well. We can actually do a pretty good job on the rest of the planet. Okay. And you can see that the mantle contribution is really quite small compared to the crustal contribution. All right. So this is how we need to refine the models of lithosphere around Juno and Jinping, 2 detectors that we have in China that we're trying to work on right now. Detector 500 kilometers to find a volume, and we refer to the lithosphere. It would be, of course, a hemispherical volume, but the mantle is 1,000 times less bright. And so it's really the lithosphere. And when I say the lithosphere, it would include the lithospheric mantle, which is usually contributing about 1 TNU. So it's really not the big player, but it's still significant. So here is Sudbury, Canada. Here is Gran Sasso, Italy. Here is Japan. And in fact, these are from the Geological Society, the Geological Survey of Japan. They've collected about 1,000 and maybe 1,500 samples from all over the country. And they've produced a map of the uranium abundance at that surface point on the Earth's crust and the thorium abundance at that surface point on the Earth's crust. So Japan is really well known. It's also the best place for all the seismometers. There's more seismometers there than there are almost people. There really are lots of seismometers. So this is what we do. And we try to voxelate the Earth. And really by voxels, we all might be familiar with pixels. Voxels are 3-dimensional units. So pitches are 2-dimensional, X, Y space, and voxels are three dimensions. And so you can divide the Earth up into a sub-infinite number of volumes, voxels, and say, I'm going to place this many atoms of uranium. And scientifically, what we do is we place them into the center of that voxel for our global model of the Earth, okay? Each voxel, we assign material density, Vp, compression wave velocity, Vs, shear wave velocity, heat flux, chemical composition. And so we're characterizing the entire Earth in that sense. And we change our resolution as we get closer and closer to those 500 kilometers. So to make it simple, we've made a box. And this box is called the continental crust. This box is called the oceanic mantle, oceanic crust. And everything beneath it in these 2 green colors is the mantle. And we have a very simple model. We know it's wrong, but it approximates the problem reasonably well. We have the pleated mantle, if you will, the source region for mid-ocean ridge basalts sitting on top, and the source region for enriched basalts like Hawaii sitting at the bottom. But the important business is right here. And we've turned the continents into about 9 layers. We have the first 3 layers representing sediments, then layer 6 represents the upper crust, middle crust, lower crust, and then we have CLM, the continental lithospheric mantle. Okay. And you'll see things like RNG 2014. For the global situation, we just simply used Rudnick and Gao 2014 to treatise of geochemistry for what is the average upper crust, average middle crust, average lower crust uranium and thorium. Then we use Bill White and Emily Klein's estimate for what is the oceanic crust composition. And we use Terry Plank's compositional model for the sediments in the ocean. Okay, so we're just pirating everybody's ideas and putting it into this big blender and come out with results at the end. And for that, we build models. So here you can see the boric CO detector in Italy. the Camland detector in Japan. And at the very, very top, you can just barely see it, the Snow Plus detector in Sudbury, Canada. I've been in that detector several times. I'm not in the detector. I've been down to the laboratory, 2 kilometers underground in the Creighton nickel mine. You take the elevator down with the miners. They go to work that way. And I go to the lab that way. And then down 2 kilometers, I walk 1 kilometer to get to the lab. I then take off all my clothes, not because I'm a crazy person. And I then put on their uniforms. But before getting to the uniforms, I have to take a shower. I get on the other side. I then put on the one-piece suit. And then I walk out of the cleaning area and I take another shower. It's a shower of air. And this is 2 kilometers underground. Something about the size of this institute is a research laboratory that is a highly clean facility in a mine that's actually actively getting nickel. So it's quite an interesting place. And the Camland detector in Sudbury is going to come online fairly soon. We're talking maybe in February of next year, something like that. All right, so then we're left with Jinping and Juno. Juno is an experimental particle physicist. The Chinese have invested about $500 million. We're talking real money here. And $500 million is really, am I online? They're trying to get a Nobel Prize in physics. That's their driving force. And they're not interested in the geoneutrinos, but they're interested in the politics and selling this story. And so they're measuring a fundamental particle physics measure, but they say, hey, guess what? We're also doing geology. So give us some more money. And I say, take me along. And really, that's what these 2 detectors are. So this is going to be about, so this is 1 kiloton. This one is 0.3 kilotons. Maybe in 3 years, this will come online and it's 20 kilotons. And this one, maybe about 6 or 7 or 8 years, will come online and it will be 5 kilotons. So by 2030, I'll be happy to come back, Juan Pablo. And the whole story will be dramatically changed. And we will really have insights into the composition of the Earth. I mean, when that one comes online, within a half a year, it will have more events counted than all of the events from here, there, added up over the decades. That's how dramatically the story will change. So this is a little bit of the details. This is sort of 50% from what we call the near-field crust, which is the first 500, and about 30% from the far-field crust. And what you can see here is the mantle contributes approximately 20% to all of these detectors. So the mantle is far away and very dim, and it gives about the same signal. So it's okay for doing the mantle, but not great. Now, this is the Jinping detector right here, right on the slope of the Himalayas. So I've been to this. There's a very large water reservoir event. So in Chinese style, they had this mountain with the river going like this and then coming around the mountain, coming down there, and that's about 70 kilometers. But they drilled holes right through the mountain. They have 6 of them, 4 of them for carrying water and 2 for traffic going this way versus going that way. The tunnels are 17 kilometers long. And in the middle of the tunnel, it's about 2.5 kilometers to the peak of the mountain. And the Department of Applied Engineering at Tsinghua University saw this on television one day and said, can I use some department money, not the kind of money you have here, but can I use some department money and have the contractors build a laboratory? So they took $50 million of department funds, and they actually have a new laboratory for doing underground research called the Jinping Underground Laboratory in this region. And it's actually in Wikipedia. You can see it and learn about it. And that's where they're building, or they're developing the 5-ton detector, the 5 kiloton detector there. So that, but this will be our best detector on the planet. because the closest nuclear reactor is 1,500 kilometers. All others have close nuclear reactors. So what we spent a lot of time doing is actually just from our desks in Maryland and elsewhere around the globe, looking at what would be the contribution. So here we're seeing thickness and color. So 70-kilometer crust is right here. The Sichuan Basin is right here. This is actually the fastest moving place on the planet. We've got GPS measurements all over there. And they have crust that is moving 10 centimeters a year in some places. So, I think it's called Huachang or Sichuan earthquake in 2008 occurred there, and it killed some 70,000 people, that earthquake. So it's an actually very geologically active area. The crust here is estimated to be 57 kilometers thick. And what we said from our simple model, that the cell in which this detector sits will give about 23% of the signal. And so we already defined that we're going to study this area really well and predict it as best as we can. And that will then, we're going to predict the signal that this detector will measure. Then we're completely blind, sort of like 2 experiments are happening, and before the measurement, we predict the results, and that's what we're hoping for. Now let me just finish up with some thoughts about the, I'm going to read this quote for you. So this is one of our crazy politicians, Don Rumsfeld. Not as crazy as they get, though. There's some really bad ones there. But this was associated with the Iraq War, and he was the Secretary of Defense at the time. But I think it's a very, very valid quote. There are known knowns. There are things we know we know. So it's like saying McDonugh and Son, the composition of the Earth. We don't really know that. There are known unknowns. That is to say, things that we know, we don't know. And so that would be McDonugh 2014, the composition of the Earth's core. That's a big known unknown. But this is the catch. But there are also unknown unknowns. There are things we do not know, we don't know. And that's really our life in the mantle. Now, I like to listen to everybody, including crazy, I say this with respect, crazy Japanese scientists. Murayama-san is a very, very famous sort of geologist, and in the sense that he does structural geology, tectonic reconstruction, and other things. And he had a very vibrant career and a lot of great scientific achievements. And I think he's serving a very good purpose. He's right now around 75, 80 years old, and he's constantly showing up at meetings. But he has 3 sigma, 4 sigma, 5 sigma ideas out there. And so what he is saying is that sediments are subducting into the transition zone. So this would be the transition zone. This is 410 kilometer discontinuity, 670 kilometers discontinuity. These are associated with phase change, upper mantle transition zone, lower mantle. And it's been demonstrated, he actually had a postdoc back in 2010, 2012, who actually did all the mineral physics of this. And he's shown that as we get to a certain depth, we transform plagioclase and K-spar into hollandite, a dense feldspar equivalent. And it would actually be gravitationally buoyant right here. And it would just hang out there. And he says, here's Japan, here's China. This has been happening, the closing of the Pacific Ocean basin, and we have accumulated a second continent. I remember I gave this talk and Don DePaulo turned to me and goes, are there igneous men there? Who knows? Well, he has the idea that there's a second continent down and has grown as a result of subducting sediments down into the transition zone. I last year made a presentation at what we call the JPGU meeting, which is the Japanese Geophysical Union meeting in Japan. It's in Chiba, Japan. And I said, I didn't say whether or not it's a crazy idea. I'm in Japan, so I can't. But I said, we can test this with geoneutrinos. And that's the fundamentally important thing. So I told you I'd go back to this diagram, and what we have is the results from Italy and the results from Camland. And what you can't see probably is the intercept on the uncertainties goes from about 17 down to about 2 terawatts. And it's really quite uncertain. The present result says that the mantle signal is about 9 plus or minus 6. We'll see what happens in the coming years. In the coming years, what we would have is the Camland, Juno, Borexino, Snow Plus, and Jinping. So just so I'm being truthful, there's no data on this diagram. They're just my imaginations, okay? But we can predict what our uncertainties would be in the continental crust. So this would, the actual physicists can do this well, and they can get the uncertainties down. We are having problems doing this well, and it's geology. It's on our shoulders. And if we take this array, we might intercept the mantle, and we might get a BSE value. We can separate out 10, 20, 30 terawatt Earth models. And that's our, we wrote this article a few years ago, and we said that's our expectation in 2025. I might now say that's our expectation for 2030. Okay. Now, down here is a site that I have, not a site, but a signal that I haven't talked about, OBK. And what you can see is it's really close on the x-axis, meaning it doesn't have much crust. So here's to sum up the information. The open symbol one, Borexino and Camland, and these are the size of the detectors, and this is the equivalent water depth of kilometers of water equivalent. So 1 kilometer of water, the density of water is 1,000 kilograms per cubic meter, but rock is 3,000 kilograms per cubic meter. And so the physicists like to just talk in what it's a single unit, and so they talk about water being 1,000 kilograms. They don't want to hear geologists talk about, oh no, it's 2.7, 2.6. They go, no, we'll just talk about water equivalent. Okay, so this is essentially 1.3 kilometers underground. This is like 1.5 kilometers underground. This is 2 kilometers underground. This will be 2.5 kilometers, and this will be about 1 kilometer underground. And this is the array of detectors. And then also I can tell you that Chile-Argentina border, they're actually for what's called Trans-American Highway. They're actually drilling a hole through one of the volcanoes. And the joint Chile-Argentina scientists are trying to get a neutrino laboratory down there called, guess what? The Andes. AN, anti-neutrino. Okay, but I've also, since around 2006, have worked with particle physicists proposing an ocean-going detector. Expensive, very expensive. Now what you can see here is this is just drawn in. So I got 2 of the same diagrams. This would be the strength of the signal. And you can see here, Juno, which is really close to a nuclear reactor, has this terrible background. And Jinping has no, well, it has some background. You can see all the nuclear reactors around the world. There's about 440 of them. But it's mostly geological signal. And the red here is the closest 500 kilometers. So it really sees that signal quite well. Now this is a tiny signal. But actually, if you scale it to 100% of the signal, you can see 70% of it is mantle signal. And I can tell you that we've come up with this idea to have ocean bottom Camland, deep ocean, 10 to 50 kilotons, filled with the same kind of scintillator we're talking about, viewed by many photomultipliers. We can move it anywhere around in the ocean, but it has to be at the bottom of the ocean. So you sink it, count, detonate the anchor chain, bring it back up to the surface, service it, move it, sink it again. Serviceable cables, it would be cabled by plugging it into an outlet on land. So maybe a 1,000 kilometer long extension cord that's doable. We've already invested $1 million. The US gave us that to do the, let's say, ideas. What would be showstoppers? And we don't have any showstoppers. So the cost really would run on the order of $500 million. And you know, you go. There's a reason why the government might want to spend that much. If you park it off the coast of Iran or the coast of North Korea, you can watch their reactors. So there's actually applied science here. We're not interested in that, but I am interested in them opening their wallet. So this would be the crustal signal. And if I remove all those continents, those nasty continents, this is what the mantle signal would look like, and this is one of the LLSVPs. You might be able, you might not, see a dashed line running there. And that would say, if we had this mobile kind of detector, would start near the North Pole and go towards the South Pole, and would see a signal at different spots. And we could map out the mantle distribution of uranium and thorium particles. Okay, this is just talking about the details. What I was really impressed by was, think of something 2 to 3 times the size of this entire building complex, sinking 4 kilometers in 39 minutes. It's really going fast. You want, if you're a fish, you want to get out of the way. So, you know, this is the map that we calculated. It's purely a calculation. I should also say that the Russians have talked about a box sound detector. This is the image of the LLSVP, and this is our predicted mantle signal. And so you can see that the mantle signal is as low as 8 and as high as about 11. So you can sort of say 9 plus or minus 2, or 10 plus or minus 2. And we could start up here by the North Pole, pass through the Aleutian Islands, and that's what this is, the signal that the Aleutians would give. Come to the middle of the Pacific Ocean, where, if you think about it, we're 3,000 kilometers away from South America. We're 3,000 kilometers away from Australia. And we're 3,000 kilometers away from the metallic core. So in the middle of the Pacific Ocean, we can test low Q, middle Q, and high Q models. And within, I can't remember what the time frame is, but within a couple of years, we could say, this is the mantle signal. It would end a lot of debate, and the geodynamicists would now then be forced to run their mantle convection code with a single value for the radiogenic power. So, in conclusion, we're talking about measuring the Earth's radiogenic power. The Boraxino presently has a crazy number, but that's their assumed crustal contribution. I claim that the particle physicists need better geologists on their team. The experiment in Italy, in Japan says that. So what you can see is essentially as high as 40 and as low as 10. The predictions are ranging from 8 to 28 from the geological community. But I'd say the future is bright, because this detector is going to come online around 2020. Oh, I should have upgraded this. This is going to really be, I'm officially a collaboration member, so I'm supposed to say 2021. I don't think so. But these are enormous detectors, and they really have very big backgrounds. They're really hard to make. I mean, think of a 40-meter wide sphere built 1 kilometer underground, having 15,000 photomultiplier tubes hanging from the inside looking inwards. It's non-trivial experiment. Jinping, maybe 2025, the Andes, maybe 2028, 2030. And then OBK, I spent almost an hour and a half. That's why I left you last night at 9:15. No, it was later than an hour and a half. I went to bed almost at midnight last night because I was talking with the Japanese particle physicist and geoscientist, because the Japanese are looking at funding this $500 million experiment, driven by something called JAMSTEC, which is the Marine Ocean Going Service. And I've been seriously involved in these discussions since June of this year. And I've been on the GQ, which was a fun event, which is the most superior ocean drilling ship there is today. Thank you for listening.
¿Alguien tiene alguna pregunta?
I have two questions. First, how do you tell apart geoneutrinos from solar neutrinos?
Aha. All right. I thought you were going to go somewhere else with that question. I'll just go back here and I'll answer that question and this question at the same time. So you may have heard of Super Kamiokande. You may have heard of Ice Cube, which is in the South Pole. And I cannot remember the experiment that's in Mexico that's on a mountain. Hawk, that's right, Hawk. And all of these are measuring neutrinos. And the first thing you see is that this is in the scale MeV, million electron volts. The Super Kamiokande is really starting out at 10 and going up to 100 million electron volts. Ice Cube is only in the GeV, so another 1,000 times this. And it's going up to EeV, which is 10 to the 18 electron volts. So they're way off the scale. And Super Kamiokande, which is starting at around 10 MeV and going higher, are measuring the solar neutrino flux. Now, if we were looking at the PP chain, we would be completely on top of this. And in fact, it would completely eliminate the geoneutrino signal. But we are looking at antineutrinos, and what's coming out of the sun are neutrinos. And we're using a technique called the inverse beta decay. So the neutrino comes into this solution, this liquid scintillator, and it hits a free proton. And that means the hydrogen atom. So it cannot really attack a proton in a complex nucleon like carbon. So it can only really hit the proton. So it hits the proton, and if it has enough energy, it transforms the proton into a positron and a neutron. And that's two flashes of light. And the separation in time between the two flashes of light is around 200 microseconds and about 30 centimeters. And the second flash of light is 2.02 MeV, which is the binding energy for the nucleus of a proton. So you get a proton and a neutron, they'll bind, that will give you 2 MeV. So what you now have is a very critical evaluator that has an efficiency of 1,000,001. You have two flashes of light separated in time, 200 microseconds, separated by about 30 centimeters, and the second one is 2 MeV of light. So in fact, it's highly sensitive to antineutrinos. Now there's lots that come from nuclear reactors, but their average energy is around 4. So what we do is fully understand the reactor energy spectrum, and there's a lot of money going into that because it helps us to look at reactors and people that don't want us to know about the reactors. Once we can subtract that away, we then have the geoneutrino signal. So I work with the US intelligence community because we need to know each other's signal. This is their background, this is my background, okay? So that's how we know that. Even though we have 10,000 times more neutrinos from the sun right at this portion of the energy spectrum, we don't spend any time seeing them because we use the inverse beta decay method. It's an excellent question. And that places into perspective, there's lots of science going on in neutrinos. And it's actually telling us very specifically about the details of how atoms are fusing together in the core of the sun, the power of the sun. So it's telling us about the power of the sun, it's telling us about the power of the earth.
Okay. In one of your last slides, you showed the prediction of the signal from the mantle. And if I saw correctly, you have two big sources, which more
This
or less
one?
correspond. No. The map of the contribution of the neutrino signal from the mantle. Yeah, this one. So these two anomalies should correspond to the big superswell.
Yes, the LLSVPs.
Yeah, why?
What? Oh, because that's how we modeled it, but that's a very good question. So very, very early on, you saw the box model of the continental crust many layers and the oceanic crust with its layers. And then we have the depleted mantle on top of the enriched mantle. And that just says that that was a sort of standard one model, okay? Simple model. But then we said, in fact, we're going to reconfigure the bottom enriched layer, and we're going to put all of those uranium and thorium atoms in the enriched layer into the LLSVP. And that's all that is. And we took a seismological model for the LLSVP, so it wasn't just hand waving. And we then determined that volume, voxelated it, and then populated it.
This is also a way to test geochemical models.
Yeah, yes, it is. Or at least creative people's ideas.
So I have two questions. The first one is, to me, it seems that almost of the energy for plate tectonics comes from the energy of abrasion, the circular cooling, because you said that almost all the radioactive energy is concentrated in the crust. So for me, well, I understand that for your conclusion that almost all the energy required for plate tectonics comes from circular cooling. So is that right, or?
Okay, so this goes down to, where is the gas gauge?
Yes.
Where is the gas gauge? Where's that red line?
And
I will assert for you, I'll get you a second question. I will assert for you, I don't know, you don't know, and nobody in this room in the planet knows this. No, so you could, you know, listen to people, and frequently, you know, some of my colleagues in geodynamics go, we like the 20 terawatt Earth, and we use that all the time in our models, and the other models are crazy. Well, I like the 20 terawatt Earth because, in fact, my name is on a publication that says that. But, you know, for instance, a fiery colleague who once stood in front of me and said, I'm virile, has put together a 10 terawatt Earth model, and he's a really smart geochemist in Paris. He's emotional. And Don Turcotte and Jerry Schubert, really big names in geophysics, they have a 30 terawatt model. Am I going to stand in front of you and say that Don Turcotte and Jerry Schubert don't know what the heck they're talking about? Never will. I just won't. But I can tell you some very smart people don't know if this gauge is over here or over there. That's a big issue. So it's a big unknown. And in fact, the latest Italian particle physics experiment, they want to go, we got lots of radioactive power. And they're in an area, this only came out 2 weeks ago. And I had some really strong emails back to a very close friend. It was a particle physicist on this experiment. I said, so you crazy? Nobody's going to accept that model. This is really going to potentially diminish the political impact. You know, geoscientists are going to go, we know they're wrong. But no, the point I'm making, I'm writing an article right now. I'm saying that the physics is absolutely perfect. The physics is right. It's the geological model that you apply to this signal is what is being debated. So, you had a second question.
If I saw correctly, in one of your first slides, you said that Geoneutrinos study will help us to know the earliest history here. And I don't understand why. I understand that they will help us to know the composition of the Earth now. But how Geoneutrinos will help us to know the earliest history of the Earth?
I think yes. And you mean, I think this one here?
Yes.
Planet formation. It's really just trying to say, what are the building blocks? If you look, there's a factor of 2, about 2.1, 2.2 difference in the uranium contents of different chondrites. And really, we're trying to understand, at some level, the Earth in terms of the absolute concentration of uranium and thorium is very, very similar to what we would call a CV chondrite, like Allende. But then isotopically, others say, no. We look very, very much like enstatite chondrites. Well, the concentration in enstatite chondrites for uranium is really low. So what, and this is really referring to is, if we can define without question how much uranium is in the earth, we can actually say that the absolute concentration of elements is not that important as compared to the isotopic composition. So the isotopes are like DNA. And the absolute concentration is whether or not you're a big guy or a little guy or something in between. So we believe that by constraining the amount of uranium as well as doing the isotopic studies, we can define, for instance, that the Earth could be just like enstatite chondrites, but not the magnesium-silica ratio that enstatite chondrites have. Or the portion, enstatite chondrites are almost all pyroxene, but our mantle is almost, it's 60% olivine. Very, very little pyroxene. So that's what I meant by that. Really good questions.
So you mentioned that you cannot measure the potassium neutrino because
Presently, right.
presently, yeah, because they don't have enough energy to produce a positron.
To produce both a positron and a neutron. So you can think of it like a punch.
Yeah.
You know, sort of, it doesn't do anything. You go, give me another one.
So,
But this is really the kind that can knock you out. You know, so you have to have more energy. And
Yes.
potassium just doesn't have that much energy.
so my question is, have you modeled the amount of neutrons coming from potassium?
Yes. So really the way we've done that is with one of my former PhD students, Ricardo Lorevo, and an undergraduate researcher working with me, Mario, we actually put together a paper in 2009 looking at the potassium-uranium ratio in rocks, all kinds of rocks, continental crust, oceanic crust, Hawaiian Islands, the isobonin, the trans-Mexican belt. From all of that, we were able to constrain the potassium-uranium variation in mean value. And from that, we have a potassium-uranium ratio for the Earth. And in fact, not different from what was speculated in 1963 in a science paper by Wasserberg. Speculated because he actually said, these granites from Southern California look like the same Ku ratio as from the ocean. And that is a number that we've lived with for a very long time until we actually documented the whole repertoire. So we don't know how much, exactly how much potassium's inside the Earth. And some people say there's potassium in the Earth's core. And we say there's no potassium in the Earth's core. But if we can do a geoneutrino potassium measurement, we could resolve that major question, is there potassium in the Earth's core? And when we find that out, we will change the models as to when the inner core began growing, because that depends upon radioactive power. So there's a cascade of consequences that come from each one of these geoneutrino measurements.
And there is no today way to measure directly the neutrino
From potassium, no.
or for many other elements.
Well, you need to be going through beta decay. And the next promising element to measure maybe in 1,000 or 1,000,000 years of technological development is really super challenging. It would be rhenium, which would be rhenium decaying to osmium, and most of the rhenium is in the Earth's core. But instead of 1 MeV, this is 5 keV from that one. So it's right now we say it's an impossible measurement, but maybe in 1,000,000 years we'll have the technology to do that. Right.
There's a question from distance.
Listo, Your Honor.
This is kind of scary. I don't get to see the person who's asking me. This could be a Nobel Prize winning physicist.
Sí, escuchamos.
My pound arms are sweating.
¿No se animó?
No, abierto su micrófono, pero no.
Well, I've provided Juan Pablo with several papers that are really, I've begun writing papers that are for the popular science, so to help understand it. And if you're interested, these might be sort of interest, because it was very, very distant science for me. So I'm happy to try to make it more reachable, accessible. So if you want.
¿Otra pregunta? Bueno, pues vamos a retirar los
Thank you.
¿no? Y pues, bueno, esta plática se grabó, ¿verdad? Sí. Luego la subimos a la red para que la puedan volver a ver.